7:33. They're still not in, so maybe we can start. Okay, just a quick recap. Remember last week we were doing this? Okay, so we talked about the solid, liquid, and the gas, right? So solid, liquid, gas, they are the three states of matter. And this topic, particulate nature of matter, right? We are looking really into how particles are arranged, how they move, and that will determine many things. Okay. If you look at the quick summary in this table form, okay, later on what I will do is instead of letting you download the lesson notes, right, which is going to take place only after a few days, and most of the time you forget about doing that. So at the end of the lesson, I'll convert this to PDF and then I will send in the chat. So remind me every lesson to do that. At least you all don't have to miss out on the downloading of the class notes part. Okay? Yeah. And then you can get the notes immediately. So solid has a fixed shape, fixed volume, cannot be compressed. And the reason for that is because particles are packed closely, okay, together in an orderly manner. You can also say orderly arrangement. That's fine. Then strong forces, even the words like very strong forces will be better, okay, between the particles. So because of the strong forces that's holding them together, they can only vibrate and rotate about their fixed position. Do you need to write down rotate? Some schools actually told the students must write down. Okay, but otherwise, just talking about vibrating in fixed position should be fine. Liquids has a fixed volume, but no fixed shape. Okay, so why is it that it has no fixed shape? Why is it that it cannot be compressed easily? Okay, to explain that, we will look at the particle arrangement and movement. So particles are packed closely together, but not in orderly arrangement. There are forces of attraction holding the particles together, but not as strong as those in a solid. That's why particles can vibrate, rotate, and move throughout the entire liquid. So they slide over one another very easily, which is why, they take the shape of the container they are placed in. Okay? So they collide against each other. This one is not compulsory to be written. Yeah, not compulsory. Because it's already pretty obvious. Once they slide over each other, they are in contact with each other all the time. Hello, Heidi. Okay, did you rush back from school? Something like that? Yeah, then you had to get ready, right? Yes, correct, because of your CCA. Okay, for gas, does not have fixed shape, no fixed volume, can be compressed easily. Why is that so? Because particles are very far apart. They are in random motion. You even can say that they are moving freely in high speeds or at high speeds. Okay, weak forces of attraction between particles. We can also say negligible forces of attraction. So you might be seeing words like this. Both can be used actually. So particles vibrate, rotate, and move freely. Okay, so you can mention here at high speeds. Okay, the rate of collision is greater than the rate of collision in liquid. Okay, this one also not that crucial. Okay, missed out this point is fine. Just talked about moving freely, right? At high speed will be better. Now, three states of matter can interchange according to the nature of the liquid also, or the substance. Okay, why do I say according to the nature? Now, if we are just mentioning water, then basically water can melt, freeze, evaporate, boil, condense. But when you come to certain substances that do not have two different melting boiling point, meaning carbon dioxide. We were talking about dry ice last week. Okay, so dry ice is made out of carbon dioxide. Okay, the melting point of carbon dioxide and its boiling point is actually the same. That's why they don't go through melting. Okay, before they can even turn into the liquid state, right, they convert to the gaseous state directly. We call that sublimation, right? So the opposite What happens when the gas turns back into a solid? What do you call that? So this is the part we have not addressed, right? Some people know, some people don't know yet, but it's called deposition. Okay, so for example, the last question, you will be looking at ammonium chloride. Is it the last question? One of the questions you look at ammonium chloride, that is under sublimation. So when you heat ammonium chloride, the fumes actually rises up. The moment it touches that inverted funnel, it actually solidifies. Okay, so it formed this solid layer, like is a deposit kind of thing on the solid layer. So that is how you can think of deposition. Okay, so it turns back to solid when it touches the cooler funnel surface. So yes, this is actually all you need to know at your level. Okay, now question 1. If I were to download your answer, give me 1 minute. Okay. Did you all do the worksheet? Evan, you did. Good. Fiona? Fiona also. Oh, everybody did. Nice. Okay, this is very, very good. I'm happy. So the first 4 questions, no problem at all. 6 and 7, no problem. 9 and 10 also no problem. So here. Now, particles vibrate in their fixed position. What do you think they are trying to tell you? What state is this referring to? Vibrate in fixed position. What state will this be? Okay, yeah, the moment you see vibrate, right? So you have the word vibrate and then fixed position. Definitely we are addressing the solid particle movement. Okay, now particles have extremely strong attractive forces. So extremely strong. When you see such words, right? Okay, telling you very strong, extremely strong, again, we are talking about solid, okay, or referring to the solid particles. Particles increase in their size when heat is applied. Now, this is a totally wrong concept because particles increase in their size. Wrong. Only the space between them, okay, or the distance between them can increase. Space between particles increase only. Okay, when heat is applied. Okay, the particles remain the same size. So liquid particles arrange in irregular manner. Yes, that is true. Okay, question 2 now. This one is quite interesting. Following diagram show the mixing of 2 liquids. How did you all derive at the answer? Okay, how do you all derive at the answer? See, assuming no loss of liquid, right? Final volume is less than 60. Isn't 25 plus 35 going to be 60 cubic centimeters? How come it is 58.5? How do you all derive your answer, which you put down in the bottle? I saw all of you got it right. But by elimination, Evan, very honest. I like honesty. Seriously, even if let's say you don't know, you guessed it right. You don't pretend that you already know. I like that actually. So at least I'm aware. Okay, this is just a smart guess. So for your case, it's elimination. Heidi, how do you get your answer? Because you know. Is that right? You also guessed it. You guessed it? How about Fiona? You guessed it also? Cannot be, right? Evan went by elimination when he got this answer. So option A, use of different sizes of measuring cylinder affect the results of mixing. Use of different sizes of measuring cylinder. Wouldn't So this one is obviously wrong. So Evan must be going like that lah. Obviously wrong what? So you cross out. Okay, so let's look at B. Particles of X and Y pull tightly together as a result. Okay, yeah. Contract, liquid mixture contract. Wow, even worse. So if by elimination, it's very obvious to be C, right? Okay, liquid do not mix well. If they do not mix well, do not mix means they form two separate layers. But will that actually cause the volume to decrease suddenly? No. This is also okay. So you chose this because of elimination. The rest all don't make sense, right? Read here, the particles of X take up the available space between particles of Y. Now, I can illustrate using this. Let's just focus on the liquid, okay? Focus on the liquid. Do you see that there are actually spaces between the liquid particles? So we assume this is Y. Okay, so X is poured into Y, right? So I have maybe the liquid particles of X now. So when I pour it in, because they are free to move over each other, right? So the space, right, can be occupied by something else if it's slightly smaller, because particles don't have the same size, right? Okay, some of them are smaller, some of them are bigger. So in this case, I can have quite a number of, see, this X particles fitting into the space nicely, right now. Then when these spaces are being filled up, then you can have the rest, then you just keep drawing upwards, and that will eventually, let's say, give you a certain volume, and that is 58.5, something like that. I referred to the question last year about sand taking up spaces between the rocks. Yes, very good. So you remembered something like that, right? So you also have seen maybe some of the motivation workshop. They will give you things like, okay, put in the big rocks, correct? Then you pour in the smaller pieces, they will fit into the space nicely. But if you start with the small sand, small particles like sand, so you form the layer at the bottom, it fills up so tightly and it's so packed, you can't add in anything in between. Then you put the bigger pieces in. There are spaces that are not being occupied. Then you put the big rocks in. So you need a very big container, right, to occupy or to store all the different particle size. But in this case, we put the big ones in first, then we pour the smaller ones, it can fit the space nicely. We can also refer to that. Heidi, were you thinking of that previously? We talked about it, right? That video. Okay, so this is what is happening here. And when you learn this already, right? Okay, you will see this kind of question being asked in Sec 3 also, even Sec 4. Okay, so now and then they do ask, there are space. So they're just trying to let you come to this concept, right? Okay, arrive at this concept, the space between liquid particles are bigger. So bigger space lah, compared to the solid. Okay, so compare solid, more space between the particles. So if you can relate to this, wonderful. Okay, question 3 now. 3 and 4 also okay. Substance changes from the state in which particles are arranged in a disorderly manner at 25 degrees Celsius to an orderly arrangement. The moment you see orderly arrangement, we know that this is referring to solid. But if I'm going to point to this one, disorderly arrangement, okay, do I immediately assume it is liquid? Can it be a gas? Is it possible? Disorderly arrangement. But why are we so certain it must be liquid? Why are we so certain? There are actually certain words to look out for. If you want to be very sure, right? Okay, this is actually, okay, must be the liquid state. How are we so certain? Now, if, okay, you see words like this, disorderly manner, or maybe they add in words, disorderly, widely spaced manner, then we can say that definitely we are talking about gas. Because gas particles are arranged in disorderly manner also. They are always moving anywhere they like, right? Okay, so if you add in words or you see words widely spaced, it's very obvious. But in this case, they never say it. So that's why, okay, can be quite sure this must be liquid. All right. So that's why this is wrong. Okay, it's not a liquid at 10 degrees, should be solid. Okay,